All right, let's take a look at page 268, number 14, which was, that was the challenge question for us, right? Anybody happen to get 14 by any chance? The answers for these are in the back of the book, so if you checked the back of the book, you'd know if you get the right answer. Anybody maybe not know what the answer is, but relatively confident maybe that they got that question? Think you got it, Brian? Okay, good. Tough question. It's a good question, though. Let's take a peek at it now. When you look at this question, is there something that you know about this question? Something that jumps out to you? Maybe a word, maybe some kind of concept that you recognize here, something that gives you a place to start on this question. Okay, I'm not asking you, how did you get the right answer to this question? I'm asking you, is there something that you know about this question? Anything that you know about this question? Tony, was your hand up there? No? Okay, good. That's something. Okay? That's not going to go a long ways in getting us the strategy for solving the question, but it's certainly something that we need to be able to do in order to solve this question, okay? We need to convert RPMs to revolutions per second. So we know that's a frequency, right? 200 RPMs ends up being equal to, it's revolutions per minute. We want revolutions per second. We're going to divide that by 60, right? 200 divided by 60 is going to give me 3.33, I think. Is that right? 3.3333 revolutions per second, or we'll just call it hertz, right? 3.333 hertz. Good. Okay, that's something. Is there anything else that jumps out to anybody as maybe a place to start here? Anything? Yep. Okay, so it gives you the radius of both circles here. What are we going to do with those radiuses? Anything that we can calculate with those radiuses? Anything that maybe those radiuses can be useful for? Okay. Finding the velocity or the speed. Okay, let's see here. Can we find the speed? B is equal to 2 pi r over t. Yeah, we can actually. Yeah, we can find the speed of both of them. We're going to call this number 1 and number 2. Let's say V1 is 2 pi r over, oh wait, we don't know what t is, do we? We know f, oh wait, we know the frequency for the, which one is that? Yeah, they both have the same speed, but they both have different frequencies, right? So we're looking, we've got the frequency of the smaller pulley, that would be F1, right? And we can go 1 over F is equal to T. So 1 over 3.333, what's that equal to? Zero 0.3, exactly. Okay, 0.30 seconds. Turn on and plug that into here. 2 times pi times 0.10 divided by 0.30. And what does that equal? 2.0944 meters per second. Good, thank you. All right, okay, there's something. Okay, you may not know where to go from here. That's okay. I mean, I hope you do know where to go from here. I hope you're able to solve this problem. But if you've got this far, you've just solved for something, and it's correct. Even if it doesn't lead me to the answer, what you've done is correct. It's not what we're looking for, but it's correct. The speed of the smaller pulley is 2.0944 meters per second. Now, I heard somebody say this just a minute ago before we calculated that speed. Somebody said, Stephanie, they both have the same speed, right? The pulley belt is on both of them. You can't have part of the pulley belt on this one going at a certain speed, 2.0994 meters per second, and the same pulley belt on this one going faster or slower. The speed has to be the same. The entire pulley belt has to be traveling at the same speed. So we know what V2 is then. V2 is 2.0944 meters per second. All right. That's something too. What else? Is there anything else that at this point anybody knows what to do? Yep. Okay, let's find the period here. T is equal to 2 pi r over v. It's not what I'm looking for. Maybe it leads me to what I am looking for. Maybe it doesn't. It's okay because it's valid and it's something. Usually, Zane, when you solve for something, it is going to help you, right? Not always, but usually it is. It's worth a try at least. So we get 2 times pi times the radius of the second one is 0.25 meters. The speed of the second one is 2.0944 meters per second. What do we get for the period there? Yep. 0.7499 seconds. And now we're going to solve for the frequency, right? F is equal to 1 over period. 1 over 0.7499 seconds. What do we end up getting for that? I'm thinking about 1.45 or something. 1.45, 1.5. 1.33. 1.33 hertz. So the first one is spinning at, what do we find that was? At 3.33 hertz. The second one is spinning at 1.33 hertz. Done. Done. Okay, did you notice how we solved that problem? First of all, did you notice that you guys solved the problem, not me? I didn't do anything in that other than ask you, all right, what could we do? That's the only thing that I asked you in that question. You guys gave me everything that we end up doing here. And did you notice that all the steps that we came up with here, somebody different gave me all those steps. So we didn't necessarily even have a clear strategy for solving this other than let's do something. Let's do something that we know. Okay, we did something that we know. Then we did something else that we know. Then we did something else that we know. And guess what happened? Lo and behold, we ended up with an answer. You get a question like this that's challenging. And that was challenging. That was a challenging question. If you saw that on a test, that would be the hardest question on the test probably. You get a challenging question. Don't be scared of it. Just do something. Do something that's valid. And then see what happens. Okay? Oftentimes you end up getting an answer. Yep. Honestly, that's probably a little bit more than what you'd see on a test for this concept. But every once in a while, I do throw a challenge question on there. Probably not quite that bad though. It's a good question though. I do like it. All right. Any more questions on those chicken and fried questions? We're all good. We're all good with those. All right. We're going to shift gears a little bit today. We're still in the same unit on circular motion, but it's really not called circular motion. It's called circular motion and gravitation. We're going to start talking about the motion of planets and how planets revolve around stars and how moons revolve around planets and so on and so on and so on. How satellites go around the Earth and how satellites go around the sun and comets go around the sun and so on. You think, what does that have to do with circular motion? Why are we doing gravity, in the context of a circular motion unit? Well, it's because the circular motion or the near circular motion that's experienced by the Earth as it goes around the sun, and the near circular motion that's experienced by the moon as it goes around the Earth, is caused by gravity. Remember we talked about centripetal force being caused by something else. In the case of a car going around a turn, it's friction. In the case of the keys going around my head, it's my hand. In the case of the Earth going around the sun, it's gravity. We're going to talk about gravity here now over the next several days because gravity can cause circular motion. And most of what we do over the next few days is going to be that gravity causing circular motion. Let's give you a little bit of a lead up to that first, though. Talk about the development of our current understanding of heavenly motion. And by heavenly motion, we mean the motion of planets generally around the sun. Let's go way back, like literally way back about 2,500 years to the time of Aristotle, 4th century BC. And then Ptolemy essentially reiterated the same thing 140 years after the birth of Christ. Yep. I'll write this down. Yep. We started off with a geocentric theory. What do you think geo means? Geocentric. Geo means Earth, yeah. The geocentric theory says the Earth is the center of the universe. And that seems silly to us. We all know that the sun is the center of our solar system, that the Earth and the other planets revolve around the sun. How do we know that, though? How do you know that the Earth revolves around the sun, Brian? Somebody told you. Exactly. Okay, that's the answer I was looking for. You know that the Earth revolves around the sun because somebody told you. And guys, you know what? That's how I know the Earth revolves around the sun too. I'm not smart enough to figure out that the Earth revolves around the sun by myself. I didn't figure that out. My teacher, way back whenever, told me that the Earth revolves around the sun. Okay, when I get up in the morning and I look up in the sky, I see the sun rising in the east. And then later on in the day, I see the sun in the south. And Seth, right now, sitting by the window, sees the sun kind of in the southwest as it's shining in his eyes. Doesn't it look like the sun is revolving around the Earth? We think Aristotle is crazy, right? The geocentric theory. But if nobody told us differently, that's what we'd say too. We'd say the sun revolves around the Earth. We know now that it's not the case, but we know now that it's not the case because somebody else told us it's not the case. So it's not so far-fetched. Okay, as far-fetched as it seems, it's not that far-fetched that the Earth would be the center of the universe. The sun and all the other planets and all the other stars, it should say, revolve around the Earth in circles. We're going to fast forward a couple thousand years to the 1500s. Copernicus, 1543. The heliocentric theory. What does helio mean? Helio. Not geo. It's not the Earth-centered theory of the universe. Yep. It'd be the sun-centered. So the Earth and all the other planets revolve around the sun. Now we're getting closer to what we believe today. Okay, the Earth revolves around the sun. There was a lot of controversy about that, by the way, back in the 16th century. Now it's just accepted. It's the way it is. We have so much evidence to support this now that there's no refuting it. The heliocentric theory, all planets, including the Earth, Mars, Jupiter, Venus, and so on, revolve around the sun. Let's fast forward another 50 years-ish. Tycho Brahe. This is kind of an odd one. You'll never forget this guy. I'll tell you a little story about him in a minute here. He observed the stars. He observed the planets. And that's it. He took some measurements. He had an assistant named Johann Kepler. Johann Kepler becomes a pretty big name a little bit later on. Johann Kepler did a whole lot of stuff with astronomy. Came up with 3 laws that describe the motion of the planets and so on. Tycho Brahe, along with his assistant Kepler, made these observations, naked eye observations. What does that mean? Didn't have any fancy equipment. We just looked up. They just looked up and measured things, different amounts of time that it took for this heavenly body to go from here to here, and angles, and so on and so on and so on. They put all this data in a book, basically. That's it for Tycho Brahe. The interesting thing about Tycho Brahe is not so much what he did, but how he died. What he did contributed to our current understanding, certainly, of our solar system. But he didn't actually come up with any theories. He just took some measurements. Johann Kepler was the guy that actually came up with the theories. Tycho Brahe did contribute, though, by collecting that data. As I say, the interesting story is how he died. So Tycho Brahe's at a dinner party one night. Listen, we're talking about the 16th century. So dinner parties in the 16th century aren't what they are in the 21st century. Okay, you go to somebody's house, you're having dinner. Okay, the formalities are all different. Everything's different about it, including when you got to go to the bathroom. Now, if you got to go to the bathroom, you excuse yourself, you go down the hallway, you go pee, and then you come back up and sit at the table and you keep carrying on your conversation. 400 and some odd years ago, if you had to go to the bathroom at a dinner party, you had to go outside. because they didn't have indoor flush toilets 400 years ago. So Tycho Brahe's sitting at this dinner party. He's got to pee, and he's got to pee bad. He's got to go really, really bad. Everybody knows what that feels like, right? Got to pee really, really bad. And he held it, and he held it, and he held it. And he thought it would be rude to excuse himself from the table, to get up and say, excuse me, I got to go pee. So he sat there, and he sat there, and he sat there. So long, in fact, that he got infected. He got a bladder infection. And 400 years ago, they didn't have antibiotics like they have now. You get a bladder infection now, it happens and hurts, and you get antibiotics, and then you're cured a couple days later. 400 years ago, he died. He died because he held his pee. So here's the moral of the story. If you got to go to the bathroom, go to the bathroom. Okay, you don't want to die because you held your pee. So we're going to refer to Tycho Brahe from now on as the pee guy. Okay, the guy who died because he held his pee. Oh yeah, also the guy who contributed to our current understanding of the solar system by taking naked eye observations of the planets and stars and so on. Then we got Kepler. Kepler, who went along with Tycho Brahe kind of because Johann Kepler was Tycho Brahe's assistant. By the way, Tycho Brahe, a bit of an odd guy, right? Dies because he holds his pee. His nose was like a silver nose too, like literally silver. Like not like silver colored because he painted it, but made of silver. Because he had an argument one day with some mathematician guy about some math problem, and they couldn't decide who was correct. Tycho Brahe said, "I'm right," and the other guy said, "No, I'm right," and "I'm right, no, I'm right." No. So they fought over it, and they decided the way they'd settle this, they'd have a duel. They have a duel, and Tycho Brahe lost because he got his nose cut off. He replaced it with this literally nose made out of silver. That's what he had for the rest of his life until he died by holding his pee. Johann Kepler, his assistant, used Tycho Brahe's data along with the data that he helped collect and described the motion of the planets. Now this is big. This is important. He described how these planets move around the sun. Remember, Copernicus said the Earth revolves around the sun. Johann Kepler described how the Earth revolves around the sun and how other planets revolve around the sun. He derived 3 laws that describe how the Earth revolves around the sun. The first of his laws is called the law of elliptical orbits. Now, hold on before you draw anything here, okay? Because what you see up on the board right now should, if you're thinking about this, make absolutely no sense. There are 2 suns there. Now, I have 2 suns. One's 3 and one's 11. So it is possible to have 2 suns, but not these kind of suns. Okay, we've only got 1 sun in our solar system. So why do I have 2 drawn there? Well, listen carefully to how I describe the law of elliptical orbits. The law of elliptical orbits says that the Earth and all other planets revolve around the sun, the one sun, in an elliptical orbit, such that the sun is at one of the focal points of the ellipse. Every ellipse has 2 focal points. Okay, if I draw an ellipse like this, there's a focal point we call right there, and there's a focal point right there. The sun is going to be at one of those focal points. Now, don't get this mixed up, okay? Which came first, the chicken or the egg? It's kind of one of those arguments here, almost. It's not the Earth goes in an ellipse, and then the sun says, oh, okay, I'm going to be here, or I'm going to be here. No, the way it works is the sun is right here, and the Earth revolves around the sun like this, such as the sun is at the second focal point, or the Earth revolves around the sun like this, so that the sun is at the first focal point. It's not at both, right? The Earth goes in an ellipse around the sun, around the second possible position of the sun like this. Or if the sun happens to be over here, then the sun would be at the first focal point. But it's an ellipse, any way you look at it, that goes around the sun with the sun at one of those two focal points. Does that make some sense? It'll never be in two places. And the sun doesn't decide where to go based on where the Earth goes. Rather, the Earth decides where to go based on where the sun is. So let's write that out in words here. So the law of the elliptical orbit says the Earth, and whenever I say the Earth, I mean the other planets as well, right? Not just the Earth. The Earth revolves around the sun. In an ellipse with the sun at one of the two focal points. Now, this doesn't even really look anywhere close to a circle, right? It's an ellipse. It's a pretty elongated ellipse. It's exaggerated. The real path of the Earth around the sun is much, much closer to a circle than what you see here. Okay, in fact, it's closer to a circle than it is to this ellipse. So why do I have it drawn like this? So that you can see that it is an ellipse. Okay, if we have an ellipse that I have drawn like this, okay, that's slightly elongated this way along the x-axis. It's an ellipse. But you're going to look at that diagram and think, oh, he means a circle. Okay, here you know it's an ellipse. Just understand that it's not that pronounced of an ellipse. It's much, much closer to a circle than what you see up there. The law of elliptic orbits, the first one, the Earth revolves around the sun in an elliptical orbit with the sun at one of the two focal points. Confusing a little bit? Wait till you see this one. Oh, don't draw this one till I'm done, okay? Tony? Yeah. The law of equal areas. Boy, oh boy, oh boy. Well, the good news is at least we've decided where the sun is. We don't have two suns anymore. We've got the sun drawn at this point at one of the ellipses. You know, that's, one of the focal points. Let's color in the sun here so you know what's the sun. There's the sun. Here's the Earth. Now, as the Earth revolves around the sun, obviously it's going to be in a different position as time goes by. So let's fast forward. This is one moment in time. Let's fast forward a day. Let's fast forward a week. Let's fast forward 6 weeks. Let's fast forward 3 months. It doesn't matter. It doesn't matter what the time interval is. Let's fast forward a certain amount of time. The Earth is right there. Now, the Earth isn't in both of those places at the same time, right? At one moment in time, it's here. 3 months later, whatever, it's over here. There's a line that joins the Earth to the sun. In that time interval, T1 we're calling it, during that time that it takes the Earth to go from this position to this position, that line that joins the sun to the Earth will sweep out a certain area. It'll cover a certain area that we're going to call A1. Now, mathematically, that would be a tricky area to calculate. I don't even know how to calculate it because it's a crazy shape. It's one end of an ellipse. But smarter people than me are able to calculate the area of that green section there that's swept out by the line that joins the sun to the Earth. Let's fast forward 6 months. 6 months down the road. Okay, this is, I don't know, let's say March. Okay, it's March. Okay, fast forward April, May, June, July, August, September. It's September now. The Earth is over here. Well, there's still a line that joins the Earth to the sun. It's the same line, but it's longer because the Earth is further away from the sun now. Let's fast forward another couple months. The same amount of time that we fast forwarded over here. The Earth is in another position, right here. There's an area that's swept out by that line. This area that's colored green here now. If T1 equals T2, in other words, if we fast forwarded 3 months here and 3 months here, if the time intervals are the same, then A1 equals A2. In other words, during equal time intervals, a line joining the sun to the earth will sweep out equal areas. We call it the law of equal areas because equal areas are swept out by that line during equal time intervals. Does that make sense? During equal time intervals, okay, this time is the same as this time. Okay, those two times are the same. During those two equal times, these two areas must be the same. Now, we can look at that and say, yeah, that's great. The areas are the same. Yippee. What implication does that have? Why is that important? I'll tell you why it's important. If you take a look at the Earth over here, and then you take a look at the Earth over here, it's traveled a lot further over here in the same time as over here. That means the Earth isn't going at a constant speed. The Earth is changing in speed. As it orbits around the sun, it speeds up and slows down. When it gets closer to the sun, it must travel faster than when it's far away from the sun. Because when it gets close to the sun, the time interval, although the time interval is the same, the distance covered is greater. So the Earth changes speed. It's not going at a constant speed. We could calculate the average speed of the Earth going around the sun, but it changes. Sometimes it's a little bit more, sometimes a little bit less. Make sense? That's not quite uniform circular motion, is it? Well, it's not quite circular motion. The speed doesn't change dramatically, just like it's really close to a circle, but it does change. Yep. Yeah. So it would be like you running around the track outside. It's kind of oval, right? You got a whole bunch of people congregated for whatever reason towards one end of the football field. As you're running around the track, you speed up as you're running past those people at the end of the football field. Then as you run down towards the other end of the track, you slow down. So if this is the sun right here, the Earth's going around, speeds up, slows down. Speeds up, slows down. Speeds up, slows down. As it gets closer to the sun, the Earth speeds up, and as it gets further away, the Earth slows down. Finally, the law of periods. We got the law of elliptical orbits, we got the law of equal areas, and we got the law of periods. All three of these, remember, coming from naked eye observations made by the P guy, Tycho Brahe, the P guy, silver nose guy, and Johann Kepler. The law of periods says this. The square of the period of revolution of a planet around the sun is proportional to the cube of the radius of revolution of the planet around the sun. What does that mean? What does that mean? It means as r goes up, the radius of revolution goes up, the period goes up, but it's not a linear relationship. As t goes up by a factor of t squared, r goes up by a factor of r cubed. They both go up together, but not linearly. Now, you might not understand the mathematics behind what I just did. That's okay. Just assume this next step is correct. If this is the case, if step one, t squared is proportional to r cubed is correct, then we could say k, a number, is equal to t squared over r cubed. Again, don't worry about the math behind that if you don't understand it. K is a value called Kepler's constant. And the units for Kepler's constant would be, normally it would be seconds squared per meters cubed, although it could be hours squared per kilometers cubed or whatever. What's kind of unique about this is that Kepler's constant is constant, but not universally constant. It means it's constant for the object being revolved around. So in other words, if I take t for the Earth, square it, divided by r for the Earth, cube it, I'm going to get Kepler's constant for the sun. Okay, the Earth revolves around the sun. So if I take data for the Earth, the period of the Earth revolving around the sun, the radius of the Earth revolving around the sun, I'm going to get Kepler's constant for the sun. If I take t for Jupiter, the period of Jupiter going around the sun, square it, and I take r for Jupiter going around the sun, and I cube it, then I'm going to get Kepler's constant, k, for the sun. These two numbers are the same. So in other words, the square of the period divided by the radius of revolution of the Earth's rotation or revolution around the sun, is equal to the square of the period divided by the cube of the radius of revolution of Jupiter going around the sun. So what? What does this get us? Well, it allows us to find data about one planet from data about the other. In other words, if I know how long it takes the Earth to go around the sun, and I know the radius of the Earth's revolution around the sun, and I know how long it takes Jupiter to go around the sun, then I can calculate the radius of Jupiter's revolution around the sun. So it allows me to find one piece of data for one planet revolving around the sun from data about a completely different planet. Because these two numbers are equal to each other. That kind of make a little bit of sense? Good news is you're not going to actually have to do that math. Okay. The bad news is you do have to at least a little bit understand what I just said. Now, if we were looking at somewhere else in the universe, okay, let's say you got another solar system somewhere else in the universe with different planets revolving around their sun. Okay, we'll call it sun number 2. Well, Kepler's constant for sun number 2 would be different than this one. Every central body, we call it, every object that's being revolved around has its own unique Kepler's constant. Doesn't matter what data we use, whether it's data for the Earth revolving around that, or whether it's data for Jupiter revolving around that, we're going to get the same Kepler's constant. But if you pick a new object, like a new sun, then we're going to get a different Kepler's constant. The space station revolves around the Earth, right? Lots of satellites revolve around the Earth. The Earth has its own Kepler's constant. We could use t squared over r cubed for the space station, or we could use t squared over r cubed for a satellite. They're both the same, but they're not the same as what we have over here, because the Earth was our central body over here. The sun is our central body right there. Right? I think that's a pretty good place to leave it today. Okay, we got about 4 minutes left. There's no point in starting anything new, at least notes-wise here today. So you can pack up your books right now if you want.